Okay guys, up until now we've looked at finding the domain of a function algebraically. So previously, when we look at the domain of a function algebraically, we're trying to scan for quantities that have an x inside of a radical, or maybe we look at expressions that happen to have an x in a denominator somewhere. But these are kind of red flags, when it comes to stating the domain algebraically. And so when we look at finding the domain algebraically, I'll tell you, one thing we should notice with our graphs of logarithmic functions is that their domains are 0 to infinity, and so they have a restricted domain. And that is to say that it's restricted to only values of x that would cause the inside of our log to be positive. Okay, so if that's the case, then what I'm here to tell you is that we have to be careful. If we ever have an expression in x inside of a logarithm, we have to be sure that what we put in there is only positive. And I suppose the reason behind that is just because, let's say if I had, say, log base 2 of x equals y. If I were to plug in, say, a negative x value, so let's say negative 1, this would be the same as 2 to the power of y equals negative 1. And what you can see is a positive base to a power could never come out to be negative here. And so if that's the case, then we can't allow the inside of a logarithm to be negative. So if there is an expression in x inside a logarithm, we must take the expression, set it greater than 0, and solve for x to find the domain. So here's the thing. The inside part of our log must be set greater than 0 and not greater than or equal to 0. And for the same kind of reason as what we did with negatives here, the fact is, if you were to say, let's try to do, say, like log base 2 of 0, that would be the same as 2 to the what equals 0. There's no exponent that I can raise a positive base to the power of and get 0 for an answer here. So just really quickly here, we say recall that y equals log base b of x is only defined for b, or our base, being positive and not equal to 1, and for positive x values. Therefore, to find the domain of logarithmic functions, we need to find all x values, or all values of x, such that x is positive. So what we're going to do is, if we ever have an expression in x inside of a logarithm, we're simply just going to say it has to be positive, and so set it greater than 0. If we solve this, I suppose we would get x greater than negative 3. And so this is right here would be our domain. One thing that I want to make sure you do for me, though, is we write this as an interval. And so as an interval, we would say negative 3 to positive infinity would be the domain of this function right here. And it would be really easy to see if I pop this over to Desmos here. If I were to do, say, just the natural log of x graph, that was this graph right here. It goes through 1, 0, e comma 1, and 1 over e comma negative 1. But if I were to say, put in this plus 3 that you see here, you might already say, well, then that would shift our graph left 3, and it certainly does. So I suppose there's a vertical asymptote shifted left 3, but you can see that our graph only exists for x values that are to the right of negative 3, but not exactly at negative 3 where that asymptote is. And so that's what we're finding here when we do this algebraically. We're kind of saying, to which side of that vertical asymptote does your logarithmic graph open? So we're going to take a look at, say, this next one here. We say, well, g of x is the ln of 3 minus x, and I can't let 3 minus x be positive or be negative. So we're going to take 3 minus x and we're going to set it greater than 0 here. Now, a couple ways to do this. One way to do it is to subtract the 3 from both sides, and so we get negative x is greater than negative 3. And then we have to divide both sides by a negative 1, which, if you remember from your algebra class, means that you also have to switch this symbol to be less than. So this would be our domain here. Or in other words, negative infinity up to 3, but not including 3. Okay. Now, with respect to, that's one way to do it. The other way that I would refer to is just, we could have added the x to the right-hand side here, which, if you look at it, would have avoided having to divide by a negative in the first place, and we still get that x is less than 3 in this case. Okay. So you get the same thing, but what we're looking for is what causes the inner part to be only positive. So in this case, I would have to say x cubed is greater than 0. Well, to solve this, we would have to take the cube root of both sides. But the cube root of 0 is only 0. And this would just go to show that our domain here would be all x values greater than 0. So our domain for this last one here would be from 0, not including 0, out to the right to infinity there. And that would be an easy one to go and look at. As a matter of fact, I'm curious, what would ln of x cubed look like? Suppose it just looks like this right here. So it looks like your basic parent function, but vertically stretched if you ask me. Cheers.